So we shall use the chemical template polymers with metric unit. So let us use this template, because if we use the template, then all the materials associated with the polymers will be available for us to pick and choose. So we open it. Okay. So we have to choose the components. So what are the components? The first component is styrene. Now styrene doesn't come only once. Styrene comes 3 or 4 times. Let us see how many times styrene comes. Here, styrene is a monomer. Then styrene should be considered as repeat type segment, and it is a co-initiator too. So 3 times styrene comes as styrene itself. And we also have polystyrene, because styrene is polymerized. So what we will do, we will look for styrene and then we shall call them 4 times. So first, this one. So add component. This is the first time. Then again you add another styrene. Then this one is styrene R, because we have to look for a segment. Okay. So this is the third component, styrene R. And we have to choose polystyrene also, because styrene is polymerized. So that way 4 times we have chosen it. So this is the conventional styrene. Let us go with styrene. Then let us choose it as co-initiator. Okay. So we have taken styrene, co-initiator, and this is segment type, right? Styrene should also be considered as repeat type segment. So this is sty-seg, and we take it as segment. And this one we write as polysty, and this is our polymer. Got it? So we have defined styrene in 4 ways. One is conventional styrene, that is monomer. Then styrene also as a co-initiator. Then styrene as a segment, and polystyrene as a polymer. Okay. So we have taken care of this one, this one, this one, and this one. 4 times styrene. What are the other things we have? We have ethyl benzene. So let us find that ethyl benzene. Here it is. Then we have N-dodecyl mercaptan. And we have di-T-butyl peroxide. So did I take all of them? We have taken styrene, polystyrene, ethyl benzene, dodecyl mercaptan, TBP, then styrene segment, styrene co-initiator, and water. I don't know whether water will be necessary or not, but there is no harm in taking the water over here. We'll rename some of them. We'll write it as ethyl benzene. This one we'll write it as DDM, and this one we'll write TBP. So this is DDM and this is TBP. Okay, so we have defined our components. One of them is segment, another is polymer, and other things are conventional. Now press next. Right. Now it comes to the polymer section because we have defined the polymer and it is asking us to define the segment. So segment, which one is the segment? Seg and type. So styrene segment comes as a repeating one. So it is repeat. Okay. It is not end, it is not branch 3, it is not branch 4. So it is repeat. Right. Then we come to the polymers. Polystyrene is the polymer, so it is polymer ID is polystyrene. Built-in attribute, free radical reaction, because in our problem we use free radical kinetic model. So we have to choose free radical selection. The moment we choose free radical selection, this attribute list will come up. What are those attribute list? This is segment fall fraction, segment flow. This one is polydispersity index. We have been asked to calculate this, right? We have been asked to calculate the polydispersity index, weight average molecular weight MWW and number average molecular weight MWN. So these two things are also there. You see, this is number average molecular weight and this is weight average molecular weight. So all those polymer attributes are there. The moment you choose free radical selection, they will automatically come up. They are attached to it. Then we have to choose the specification methods. So the method filter is polymer because we have taken the polymer filter and these base methods are available and we have to choose poly NRTL because that's what we have been asked to use, poly NRTL property method. So we choose poly NRTL. Okay. And then comes the parameters. Now we have a pure component. TBP is a pure component with molecular weight 216.32. So we'll assume this as a pure component. So go to TBP and parameter MW component TBP and its molecular weight is 216.32. So it is 216.32. Now, you may or may not specify this TBP over here because this particular component, that is di-T-butyl peroxide, this is a conventional component. So already Aspen Plus has its information. Like what is the standard molecular weight, Aspen Plus already knows. Okay, so you do not have to give. But suppose you have some extra information about TBP, which you have. In your model, this TBP has been identified with a molecular weight of 216.32. So it may not be the same as what Aspen Plus knows. but you have to override the information of Aspen Plus. So you are externally adding this molecular weight information and asking Aspen Plus to use this one, not the one which it has its own database. Okay, that is the reason you have given this pure component molecular weight of TBP. Right? Now you can press next. Required properties inputs are complete, so you can run. Yes, the results are available. So property estimation is complete. We can go to the simulation. Okay. Now in the simulation, we have to add these reactors. So there will be 3 reactors. There will be a flash after that, and the polymers will be taken out of the flash, and unreacted styrene will be fed back through a heat exchanger, and it will be recycled along with the makeup. Okay, so the entire flow sheet will take over here. But before that, let us learn something about the reaction mechanism, because we do not know anything about the free radical mechanism other than whatever it has been provided. But whatever it has been provided over here, we have to learn, because we cannot use them blindly. But anyhow, first press new to identify a reaction. Okay, so what are those reactions? In general, we have learned how to use general reactions, power law, LHHW, but we have never come across a free radical reaction. So this is the first time we are going to choose free radical reaction in our course. So once we choose it, press OK. Then these are the options open for us. Now we have to pick and choose. First, the polymer has to be selected. Here we select polystyrene. That is the only polymer that we have. So this is the polymer. Now we have to choose monomers. We have these options. What is our monomer? Our monomer is styrene. Right? And this monomer goes to a segment. We have to form a segment, right? So this is the segment. And this segment is repeated. Styrene after styrene after styrene, right? And what is the initiator? Initiator is TBP. That initiates the reaction. TBP decomposes and it initiates the reaction. Does it have a bi-initiator? No, but it has a co-initiator. What is that co-initiator? We know styrene is also a co-initiator. So we write co-initiator, it is our styrene. We don't have any catalyst, but we have transferring agent. What are the transfer agents? We have ethyl benzene and N-dodecyl mercaptan. So these are the chain transfer agent. So we have ethyl benzene and DDM. Okay. So these are the transferring agents that we have. We don't have any solvent. We don't have any inhibitor. So these are blank. Now go to the reaction. Now in reaction, you can painstakingly put the reactions over here one by one. But here in one special option is there which you can use, that is generate reaction. It is very informative. You just click generate reaction and it will generate the series of reactions based on the monomers, initiators, co-initiators, transferring agents, whatever you have given. Based on that, they will generate this series of reactions. Only you have to supply the rate constants, nothing else. So these are the set of reactions that are generated, but all of them may not be relevant for you. For instance, we have initiator decomposition reaction. Yes, we have init dis. Thermal induced initiation. That also you have the special type of initiator. It is init sp. You go to the resources and help. So you write init sp specifying free radical polymerization kinetics. So these are the supported free radical reaction types: initiation, propagation, chain transfer, beta scission, chain termination, short chain branching, etc. So here you can see the reaction kinetic scheme, that is free radical. Here you have initiation, propagation, chain transfer to small molecule termination, and the nomenclatures are, or the live polymer reactions are given over here. How it is transferred to monomer, to polymer, to agents, solvents, how the termination disproportionations work, how the termination combination works, and so on. And this particular reaction is same as whatever it has been given over here, is the same thing. Okay, so K naught is a pre-exponential factor, EA is the activation energy, activation volume, pressure, and then the initiator decomposition reaction, Kref and EA value, that is K naught, EA value, and Tref, they are given over here. And then this is the initiator decomposition reaction. Then this is induced initiation reaction. There are two types of induced reaction. One is thermal initiation, another is radiation initiation. Okay. So thermal initiation, radiation initiation, they are special type of reactions. So they are called special initiation reactions or init SP. This is init SP or special initiation reaction. Then we have chain initiation, chain propagation, chain transfer to monomer, chain transfer to agent ethyl benzene, chain transfer to agent DDM, term dis. We do not have any equation of this sort. We have chain termination by combination. So we have term comb, but we do not have term dis. Okay, so this particular equation we can omit. So we can delete this equation. So that way we have 8 reactions. So basically we have 8 reaction informations over here, so we can take them. Okay. So interested people can go through all of them one by one and learn it better. Actually, Aspen Plus doesn't have any comprehensive information, so I would advise you to go to a polymer engineering textbook where you will get more elaborate information on that. Anyway, let us continue it with the example. Now we have to enter the rate constants. So in the rate constants, we have to provide this data. Okay, so these are the data we have to provide. First one, we have to give 1.42938 into 10 to the power minus 5. Here it is 27538.9. Here it is 1.5768 into 10 to the power 9. Here it is 27 419.5. Chain initiation is 3.7836, 10 to the power 10. Propagation is also the same one, so we'll copy and paste. Here it is 7062.67, 7062.67, and this also copy and paste over here. Then chain transfer to monomer, it is 1.1916, 10 to the power 10. Here it is 12663.6. Then this one 3.7836, 10 to the power 6. Same with the other agent. Here 7067.45. Copy and paste. This one is 4.41, 10 to the power 10. And this is 1675.98. So all these informations we have entered. Then in the first equation we have Tref 333.15, number of rads 2, and then efficiency 0.8. So we have efficiency 0.8, and the chain transfer to monomer, it has TBP fraction 1. It has TBP fraction 1. So all others are by default we have chosen. And then we come to options. We are asked to assume quasi-state approximation and special initiation reaction. So we know what is special initiation reaction. The moment we press special initiation reaction, this one becomes open. We have a monomer, that is styrene, with thermal initiation coefficient of 3 for styrene. Now let us go back to our helpline. Now here you can see in the induced initiation reaction, there is thermal initiation, radiation initiation. So there are three factors, A, B and C. So here you can see coefficient A, B and C. Coefficient B is for thermal initiation, where A and C becomes 0, and coefficient B and C both are for radiation initiation, where A is equal to 0. Right? Now here we have been said that we have a thermal initiation coefficient 3 for styrene. So it is only thermal initiation. Here we do not have any radiation initiation. So for thermal initiation we have coefficient 3. That's all. Okay. And what is quasi-state option? Users may invoke the quasi-state approximation for a live moment equation. Invoking QSSA converts the live moment differential equations to algebraic equation. So that is the quasi-steady state approximation. So once you tick this option, then whatever the ordinary differential equations are there in these reactions, they convert into algebraic equation and you can solve it. Okay, so that is the option you have to tick. Okay, So our set of reactions are complete over here. Now we go to the flow sheet and build our flow sheet. Okay.